So here we go. Launching an object at some angle, v sub o, at some, well, angle. Here's the deal. First thing I want you to recognize here is when you launch something at an angle, it will have an x and a y component to its velocity. In other words, this thing will be going, let's see, let's drop straight down from here. It'll be going this fast, horizontally, VOX, which, by the way, will not change, right, throughout the entire time. So in other words, if you pick a spot right here, it's 1, 2, 3, how many blocks is that? 4? Yeah. So its x velocity will still be the same. So VOX is equal to VX all the way through this thing. You go to the top, 1, 2, 3, 4, it'll be still have that x velocity. And here it will still have 1, 2, 3, 4, it'll still have that x velocity, and even just as it gets ready to land. So that x velocity will be unchanged. The y velocity, which we will do in pink, will look like this. That's VOY. Now that will change because of the acceleration due to gravity. See, on the way up, the velocity is pointed upward, but acceleration, of course, is down, and when they're against each other, that's slowing down. So I would expect at some time later this pink arrow to be shorter, and then get shorter and shorter until it gets to 0 here, because then it starts pointing in the other direction. And now it's speeding up because the velocity is downward and the acceleration is downward. How do we find these numbers, VOX and VOY? Well, if you did your vectors over your summer assignment, you know that VOX, you're just going to take whatever this is for VO and multiply it times the cosine of the angle that you're given. And your VOY is going to be just VOY is going to be VO times the sine of that angle. But you already knew that. So as soon as I said, the first thing I'm going to do is find the numbers associated with, if I can, VOX and VOY. Alright. So let's see if we can make a guess at these pink arrows as we go through here. Here, the velocity would be in this direction, tangent to the curve. I just draw a big old line out that way. I'm going to follow my green arrow up until I get to that line, and then I'm going to follow it over horizontally, and that is how high my y velocity is. Notice it's gotten smaller. And here it's going to go away completely. Now I've deliberately chosen the same height over here. So what do I know? Because this is going to be important at the end too. This is about 1, 2, 3, a little over 3 blocks tall or so. 1, 2, 3, a little over 3 blocks tall. So guess what? By the time it gets here, what's it going to be? Well, 3 blocks, but just a little over 3 blocks, but the other direction. Because now all that's the speed it lost from here to here, it's gained coming back. So here's your VY at this point, here's VY at this point. Notice it's VY, not VOY. VO is your original, and it's going to decrease and then increase coming back. And of course here, VY is at the highest point is 0. What about here at the end? You got it. Yeah, that's right, right? There's symmetry here. We have this at a certain velocity here. We lose it all, and then by the time we come back to that height, we gain it all. So if it was, there's go, like that. Now, I will point something out. That does not mean that your VY is always the same as your VOY, just in the opposite direction. If, for example, give you a couple of examples where that won't be the case. Let's say I launch from a cliff or something, and it goes up and comes back down and goes down here. It will be the same at this location, but by the time it gets down to the ground here, certainly my y velocity will be larger than it was originally in magnitude. So we're talking about the specific case when it returns to this height that it was launched from. Of course, here's another example. What if I launch from down here and my landing point is up higher? So if I launch from here and I launch it up and it lands here, my y velocity will only be a little one compared to the initial, because it wouldn't have had time to gain it back yet. So these are examples of, not every problem is going to launch and land at the same height. So keep that in mind. All right. So what do I know about the highest point, for example? At the highest point, the key here is your y component of the velocity is always going to be 0. But notice it's not stopped because it still has the x velocity. In fact, at the highest point, the x velocity is the velocity. Ooh. I haven't seen it. Really, that's just like a horizontal projection, isn't it? See, you're really like, when you look at a horizontal projection like this one, you're really picking up the story of a halfway through in a way. Right, you're really just looking at it at the top, if that helps. If it doesn't, ignore it. So, down here at the bottom, if it comes back to the height at which it landed, well, let's see, what do I know? I know that my y initial and my y final are the same. I could call them both 0 in this case, but I don't have to. So, I'm just going to say that they're the same. But they could both be 0, they could both be 3, it'll actually not make a difference. What about my final velocity at this landing spot? Well, it's equal to VOY, except it's in the other direction. So we would say it's equal to the opposite, or negative VOY. Alright. We should be able to use that fact, by the way, to easily calculate the time it takes to go from here to here. I'm not going to do a formula or anything. I'm going to go to an example. I'm going to stop this video and then we'll go to another one. But I think for now, this is a nice overview, or should be an overview, of what's going on. The only thing I'll say is this, is if I do find, let's talk about this highest point in relation to the landing point. There's a whole lot of symmetry here. So whatever time it takes to go from here all the way to the ground, how long do you think it's going to take to get to the highest point? Yeah, that's right, half, right? What about this distance from here to here? How does that compare to the entire distance it travels? Once again, this is going to be half. So if I figure out this is, 100 meters, it should be 50 to the highest point. If I figure out it takes 6 seconds to go from here to here, then it's going to take 3 seconds to get to the highest point. So there's some information I can pull off of that. I'm going to go to a different video and we're going to actually do an example. We're going to give a velocity and an angle and we're going to work it out and see how all this looks.